Welcome to this presentation. We're going to be looking at applying bearing loads. This is the reason for this is in ANSYS and SolidWorks. Sometimes the applying different loads is really easy. Sometimes it's not quite intuitive how they have it set up. So we're going to do it for the same setup, but we're going to do it both in ANSYS and SolidWorks so you can see the differences here. And if this sheet is in the notes section, if you can find the link down below in the notes. So go download that and you can follow along with the setup and get some understanding of how to apply, in this case, bearing loads in ANSYS and in SolidWorks. Before I get into this, I want to show a video first. This is from SolidWorks, and it's on testing handcuffs. And go over here to it. And the point of this I want you to think about here, and the highlight of the video is how do we simulate something that we're looking at how it works. So in this case, it's handcuffs. How do we simulate how the handcuffs could pull apart? And if we're doing that in simulation rather than an experiment, how can we think about that? And so let's watch it and we'll talk about it briefly after.
As a good engineer, you understand the benefits of simulation. The ability to carry out virtual tests on your product to gain knowledge of its performance in the real world before you make it is invaluable information during the design process. So why don't we all do it? Perhaps it's a lack of confidence, or you just don't feel that you have the knowledge to set up the simulations correctly. But guess what? With SolidWorks Simulation, if you know how to set up a physical test, you know enough to set up a simulation. Take these handcuffs, for example. If asked to test the ultimate strength of a pair of handcuffs, you would probably simply put them in a tension testing machine and pull. But what if you didn't have the handcuffs, and all you have is the SolidWorks model? What now? What loads and restraints do you use? And what faces do you pick? For a novice user, there are just so many choices, it can be overwhelming. Rather than diving straight into the problem, let's use our knowledge of the physical test to guide the simulation. Just as in the physical test, let's include the grips of the testing machine. The beauty of working like this is that the loads and fixtures become very simple, and SolidWorks takes care of the rest. Once we have completed all the loads and restraints, we can hide the grips. A big advantage of using simulation is that you can slow everything down and see exactly what is happening. As the load increases, you can see the stress buildup in the fixed frame of the handcuffs. We can see the frame starting to bend until the teeth on the moving frame are pulled out of the ratchet mechanism and the handcuff is released. Although the frame still has some residual strength, our prisoner would be long gone. So how good was our simulation? Well, we took a pair of handcuffs down to the materials lab and put them in a tension testing machine. Just as in the virtual test, the handcuffs look good until, with the gentlest of pops, the teeth pull out at a load of 5 kilonewtons. If we continue to increase the load, the handcuff frame takes all of the load until the ultimate failure load. Comparing the physical test and simulation, we find excellent agreement for both the failure load and how the handcuffs fail. So with SolidWorks Simulation, you can judge the impact of any design change you make on the overall performance of your product, ensuring that you achieve the best design possible. Although the simulation of your products might seem daunting at first, by using SolidWorks Simulation and creating your virtual test the same way you would do a physical test, you too can see how your products will perform in the real world without having to build expensive and time-consuming prototypes. With the physical test, all you have at the end of the day are the broken parts and a results graph for one test case. But with the virtual test, you can look at every possible result and loading scenario, time and time again, giving you a greater understanding of your product's performance so you can make good engineering and design decisions, making your products better and your customers more satisfied. To find out more, contact your local SolidWorks reseller to see how easily you can
Not necessarily making this a big ad for SolidWorks, but I did like the focus they had on their video. So, big thing I want you to think about as you move forward with simulation is that we can do a lot of the stuff we're testing or when we're developing a part, thinking about how will we actually test it in the physical case, and we can try to set up the same case in the simulation. One big piece there is figuring out how to apply the load actually on the handcuffs is a little difficult, and I've seen this before, especially when applying loads to the top of bolt heads. In their case, they drew the grips, and then they put the loadings on the grips and let the grips apply the load to the handcuffs like what happened in the tensile test machine. And so with a bolt head, you would create a wrench, or at least part of a wrench, and you'd apply the load to the wrench, and the wrench would apply the appropriate loading to the bolt head. So try to think of it from that perspective. It may actually make it easier as you apply loads in simulations that you may run in the future. All right, so let's get into this. We got the bearing loads. And we're going to do this in ANSYS. So we're going to set up we got a concrete floor and we got a wheel. In ANSYS, we're going to have concrete and structural steel for the two materials. And so let's go ahead and do that. So let's get in SolidWorks to bring those things up. So again, this is in the SolidWorks folder. You should be able to download applying bearing loads and unzip the folder, and you'll have these. Actually, I'll probably take this out because I already saved this from last time. But we want is the concrete floor and the wheel. And we actually want this in an assembly, so let me cancel out this. I'm going to do a new assembly to bring these things together. Go ahead and browse. We'll get let's bring the concrete floor first. And I'm going to green check the concrete floor here. And then we'll come back here to assembly, insert component, and also insert the wheel. And I'll just put it on top there for now. Now we need to mate this wheel, make sure it's connected to the concrete floor here. So let's come in here and click on mate. So let's get this edge right here. Make sure these edges are exactly lined up. So we'll go this edge and this edge. All right, so those look good. So now we can move it on that edge, but you see how it rotates there. So let's now mate this face with this face. All right. So again, now it won't turn, but it can still shift back and forth there. That's okay. We'll fix that when we actually apply the constraints when we do the simulation. So I'm going to go ahead and check that and leave it there. All right, so let's zoom out here. So that's the setup we want. We're going to do an ANSYS first, then we'll come back and do it in SolidWorks. All right, so we need to save first before we take it into ANSYS. So we'll save it. Yep, let's rebuild that. And we'll save it as wheel and floor assembly. All right, so now I can take ANSYS. And actually, I was looking at SolidWorks 2015. I'm using 2013. So ANSYS shows up here in my version, obviously. I believe in 2015 it shows up under Tools. And under Tools, I get the menu to show up here. A couple menus down here, ANSYS, this basically the same thing will show up under Tools. So if you have that, that may be where it's showing up at. So I'll go ahead and take this into Workbench. Again, if you have need to save it as a step file, you can save it as a step file and bring it up into Workbench as a step file. All right, so we're going to do a static structural analysis. So bring that over. And we'll link the geometries. So click and drag the geometry over. Let's go into engineering data and get our concrete. So we already have the structural steel. Get our concrete. We'll come over to engineering data sources, general materials, and find our concrete in here. All right, so we should have now concrete and structural steel. So we'll close out there. And geometry is good. So let's go into our model, double clicking there. There we go, kind of zoomed out a bit. I'll zoom in here it again. All right, so let's go put in materials here. So we're going to geometry, and the wheel we want is our structural steel. And for the concrete, we want as our concrete. So let's select our concrete there. All right. Looking back at the sheet, we got the materials defined. Let's look at the connections. We want the global contact to be no separation. So in ANSYS, it's no separation. In SolidWorks, no penetration. So no separation. So let's come back in here. So under connections, we're going to expand that and see contacts, expand that and click on contact region. So what this is saying is when we brought these two in, this is a place that ANSYS recognized that they are already contacting each other. Wheels contacting the concrete slab. And so if we rotate around here, we can barely see here, there's a red surface. Basically this surface right here on the bottom side of the wheel, down here, is in contact with the concrete slab. So that's the red surface is the wheel, the blue is the concrete floor, and they're in contact right there. So we wanted that to be is not bonded, because what that means is they're fixed, and if they move, they'll move together. They won't deflect. Those two surfaces in contact with each other, they won't deflect at all. We want them to deflect. We just don't want them to go through each other. So that's why we want to choose here no separation. All right, we don't want them to come apart and break up. All right, so no separation there. That's good. And okay, so next we have boundary conditions. We want symmetrical faces. We'll put frictionless support, and at the bottom of the floor we'll have fixed support. So the symmetrical faces is right along here where we have symmetry with the floor and the wheel. So we want all those to be frictionless. So we'll click on all those, holding down Control, get all those surfaces. So we'll come up to supports, and we want frictionless support. So that looks good there. And then on the bottom side of our concrete, that will be our fixed support. All right, so those two boundary conditions there. And let's go back here. We're going to do a loading. This is where the bearing load is going to happen. So we want to change vector to components, and we want it to be in the y direction at minus 2,000 newtons. All right, so we'll show this. So vector to components, 2,000 newtons. The bearing load is going to happen here. We said we're going to have a bearing load inside here, inside our wheel, and that's going to be driving downward in the negative y direction. So we already selected that surface, so now we can go up here to loads and do bearing load. And I'll pick up that surface because we already had it selected. And so the sheet says we're going to change vector here to components. And we want the bearing load to only be applied in the y direction, negative 2,000 newtons. And that's all we need to do to apply the bearing load there. All right. And so the last one here is the mesh. So we have the main mesh. We'll just do a medium. And for refinements, we're going to do the inner surface of the hub and the lower hull. And I'm actually going to do that after we saw it the first time. So we'll come back and do that. All right, so for the mesh, let's come in and do the globally. We'll change the sizing to from coarse to medium. And we'll leave it with that for now. All right, and let's look at the deflection. So we'll come in here and we can look at overall total deformation and see what we get there. So we're going to right click and solve. All right, so it solved it, but notice these warnings down here. It says one or more bodies may be unconstrained or experiencing rigid body motion. Weak springs have been added to attain a solution. For the troubleshooting, et cetera, et cetera. All right, so what happened here is, well, how did we constrain it? We constrained it here, frictionless on this surface, and we said fixed at the bottom. So what does that mean for the wheel? It can go anywhere. Now we did do the mating in SolidWorks, but the mating does not fix it in space. It just fixes it. It tells it where to position it in SolidWorks. It doesn't actually fix it where it's at. So we need to have this thing fixed. So because basically this wheel could slide this way, it could slide this way, because we have the frictionless support there. So we need to fix this thing so it doesn't go sliding anywhere. So we need to fix, oh, and the weak springs part, this is kind of neat. So what happens is if things start flying away, if the model, in the model it's noticed that things start flying away, it'll apply weak springs to keep them from moving. So the weak springs means that they can still move, it just means they can't take off and disappear. So it's that way we can solve our model to try to figure out what's going on. If we need to apply additional constraints, and then we can fix things before. And then ultimately we want to remove weak springs, but they're a neat thing we can start in. So again, they're virtual weak springs, but it's something that ANSYS can use to help the solution to move forward. All right, so we'll do another frictionless support on a surface over here. So let's go back here, and we're going to click this surface right in here, because that one doesn't move much. So we're going to make that one just be a frictionless support there to keep things from sliding around. All right, so let's solve this again. Hopefully we can get rid of that error. In this case, we're okay because while it is under constraint, it can fly up. It won't fly down because we say no penetration into the concrete slab. So that's our results here. So let's look at what we got here a little bit better. So we can see it's really deflecting down a lot right there, right? Well, see what's happening. This is millimeters, and we can see the maximum there. That maximum point there is 0.0025 millimeters. So really, this is probably not to scale. It's not. So if we look up here at the result, it's out of scale. So it's 1.5 times 10 to the 4th times the actual value. So if we would go to undeformed or true scale, so this is the true amount of deflection, that's what it looks like. So it really looks like it's essentially undeformed. All right, we could really exaggerate this guy. We could go 2 times. And if we want to go 5 times, right? So again, this just helps us to see where things are happening. So that was the auto scale that was being applied to it. All right, well, we look over here to make sure we see what's actually happening. All right, so oops, how'd that get in there? Get rid of that one. The other thing I said I was going to do is we wanted to have, going back here, we wanted to do the refinements here. So look at the inner surface of the hub and the lower hole. So let's look where that is. So if we go back here, and let's look at the stress too here. Where do we get the stress here? So we'll go back here and get stress, von Mises, and let's look at that one. Yeah, so we can see the kind of stress that's happening underneath here and in this area. So those are 2 places where we're going to see that we see a large gradient. Zoom in here. Large gradient that's happening. So those are places that we want to make sure we have plenty of nodes to capture what's going on there. Let's see what kind of nodes mesh we have. Yeah, that's really coarse right now. So let's click right here and right here. Click on those 2 surfaces. I can hold down control here. And we'll go into mesh control and do refinement, and we'll just leave it at 1. And let's see what that mesh turns out to be here now. All right, that's a little better. Maybe we can go a little bit more. So click this surface. Actually, we'll come back here in refinement and we'll update this. Let's go to 3 and see what we get there. All right, that's a lot better. All right, a lot more nodes in there. Still probably could be more, but I think we might, hope we didn't hit our limit here. Let's see what we got. Yeah, we're still good on the limit. All right, so let's see now if when we solve, let's look at our stress at those points there. So we'll go ahead and solve this. So now we got a better concentration there. Well, you can see the concentration that's happening. Oops, happening right there, as well as in here. And then we got the mesh to back it up a little bit. Again, the mesh could probably be finer, but you get the sense of where we want to focus in on as we do this. So let me go back to total deflection and we'll look at this thing overall. And we'll save this as we do our SolidWorks and refer back to it. All right, so let's go to our SolidWorks case now and get this thing all set up. So we're going to go to simulation and we're going to do a new study. And it's going to be a static study. So we'll green check that. Just working our way down the right-hand side here. So we're going to magnesium alloy. Obviously, that's not concrete, but it has a similar modulus to concrete, and so we use that one because that's the closest thing I was able to find in SolidWorks, so we can compare these things a little bit better. And then cast carbon steel we use for the wheel. So if we expand the parts here, go to concrete floor, right-click, apply edit material. And for the concrete, we said the magnesium alloy, so that's other alloys. So magnesium alloy. Apply that and close. And it looks like the cast carbon steel is actually already there. It was defined, I think up top here when we had the part defined. So we're just going here and confirm we're at cast carbon steel. So we're good there. All right, so we got the materials now to the global contact. So again, it already saw, well, in SolidWorks it says all contacts defined up front are considered bonded. So what we're going to do is change our global contact. Instead of being bonded, we're going to edit the definition and say they're all no penetration. So anything that's in contact, and we don't know actually what is at this point, but anything that is will be considered no penetration instead of being bonded. So we'll green check that guy. All right, so do some boundary conditions here. So fixtures, so we'll do the fixed geometry just here on the bottom. So we're going to go okay with that. And then we wanted the roller slider support for the symmetry. So we'll add some more. So actually, you can right click there. I could go up here. I'll go up here and do a roller slider. So you can click here. All right, we get all those and check that off. And oh yeah, so we might as well just get this right now so the thing doesn't fly away. I will click this surface and get that one as a roller slider too. Which one do I want? Get rid of this one here. There we go. All right, so we got those defined. And what else? So loading. All right, so let's go back here so we can see this. So we got the loading. So we're going to do bearing loads, and we need to set this up first a little bit. We're going to go assembly, and under reference geometry, we're going to put a point down so that we can define a coordinate system, because that coordinate system is needed to define the bearing load. All right, so let's go back and do that. So go up to assembly, reference geometry, and we want to do a point at the arc center. So we're just going to click this point right here. Click the edge there. We don't want the face. So delete that. We just want the edge. And we'll go ahead and check that off. So it gets a point right there. The point's needed because to define a coordinate system, which we want next, we'll do that. So go to the coordinate system now. The x-axis, well, we got 0.1. That's the big thing we want. The x-axis, the z-axis, we're okay with what we have. We basically want the z-axis. We want it to be aligned with the axis of our hole. So if it's aligned already, we don't have to do anything else. We can just screen check. It's okay where it's at. All right, so that coordinate system is already active. So we're going to go now into a load. So get the applying the load on here. So we'll come to external loads and bearing load. And so we got that coordinate system. We're going to put it on the, not that face. I'm not sure why that one keeps coming up. It must be still selected. We want the inner surface here of the hub axle. And we'll do, we don't want it the X direction. All right, so these, you can see where the X direction, hopefully slightly, there's the X. Y is up here, so we want to go in the Y direction. And we're going to do 2000. And you can see where the arrows are pointing, so that's the positive Y. We want to go in the reverse direction. And so that's the way we want to go. And I actually can tell you the distribution too. So we want a sinusoidal distribution for the bearing load. So higher at the bottom here, smaller at the sides. Or we want a more of a parabolic distribution. Again, depending on what you're looking at, you can do what you want, but we'll just go with sinusoidal, we'll go with the default. So check that off. And do we have everything else? Oh, mesh. All right, so we'll go into mesh and create mesh. And the main mesh, we're going to go with the default here, and then we'll come back and apply mesh control. So let's leave it there for now. All right, fairly coarse as we expect. And we'll go ahead and run it. All right. So the stress, here's the displacement. All right, doesn't look like it's displacing a whole lot, right? No, again, it's the same thing as the last time. All right, this one's, and actually these contours, let's get something more familiar to what we got with, we'll do some smooth contours so it looks a little bit more like SolidWorks here. So we got total deformation in millimeters, so let's compare apples to apples here. So total deformation in millimeters, we're millimeters here. And we haven't quite refined the two spots here yet, but this one's at 3 times 10 to the minus 3. This one's at 2.5. So they're within range of each other. So some of it might be the mesh quality between one and the others, might be the solver. Whoops, might be the solver between the two. But those are looking pretty comparable there, at least with the scales. Again, I don't put too much hope or trust in the colors because those are always based on the scale. So make sure you're looking at numbers when you're doing this. Okay, so let's go back and do our mesh refinement. So we'll come back up here to mesh and right click, and we'll do some apply mesh control. And the surface that we want are this inner surface of this hole, and we also wanted this spot right here. That's where we had the stress concentrations. And we'll crank this up about 3/4 of the way there. And so let's see what the mesh looks like there. So right click and create mesh. Yeah, so it's a little bit more fine in there. Up here and run. Trying to get a face so we can see things going on here. There we go. All right. So yeah, we got the stress concentration in there. And now, that's the von Mises, what's the displacement? So 3.165. All right, again, we're in range, but there are some differences there. So let's go back to the stress here. And compare that to what we have here. 2.4 megapascals. So 2.7 megapascals. So yeah, so that's the comparison. Just wanted to show you how to do bearing load. If you have any questions, let me know. But hopefully this gave you some understanding of how to do that and applying boundary conditions, setting up meshes and other things for models in both SolidWorks and ANSYS. So till the next presentation, see you then.